So Ben Letcher, you're up. Welcome. Ben is an ecologist, many of you know, at the USGS, working in fish ecology and models, environmental drivers of stream ecosystems and data systems. And he is going to share with us towards joint flow and temperature models for the Northeast. Thanks, Ben.
Everybody, it's great to sort of be there and be with you. I really miss the lunches at NCTC, so I hope everybody had a good lunch. So I'm going to talk about flow and temperature modeling in headwaters. And before I get going, I'd like you to think a little bit about how you might make decisions differently or do your job a little bit differently if you had estimates for the estimates of flow for the tributaries that you cared about. And that's what we're working towards, is trying to get estimates of flow and temperature for tributaries that people need to make decisions about. So there's a great group of modelers and others that I'm working with on this project. And really what we're doing is focusing on headwaters and thinking about headwaters where the brookies are for the most part. And they're important, we all know that, but they're understudied. This chart shows the distribution of gauges, of USGS stream gauges over here that are out there by stream, that are out there by stream order from the smallest to the biggest. And you can see these are the ones that are gauged, and most of them are in fourth order streams, but very few are in first and second. And compared to the number of streams that are out there, there's really very few of the headwaters that are gauged. So what I want to ask in part here is how do we flip this chart? How do we get more of these smaller streams monitored for flow and temperature as well? We also all know that these smaller headwater streams are under threat. And a lot of this, it comes down to the idea of kind of a climate squeeze where we think it's going to get hotter down below and have more variable flow up above, floods and droughts. So the fish in the middle, or fish are going to be forced more into the middle and be squeezed by climate in the future. The other thing that we know that we're learning more and more about, that there's lots of variability among headwater streams. Dan Hitz talked about this a bunch. He showed you some earlier. There's lots of variability in flow and temperature at very small spatial scales. So when states and others are trying to think about which ones might be climate refugia in the future and which ones to protect, it can be really daunting when you have this very high level of variability at a very small spatial scale. So this is more reason to be able to estimate what's happening in these small tributaries. And we have this high amount of fine scale spatial heterogeneity in both temperature and flow, and temperature is mostly from groundwater, and flow, it mostly comes from local processes and a little bit by weather, but mostly from flow. So this is a recent project that Dan and I and others have been working on called the Eco Drought Project. It's across the US, and we have some focal areas that we've been working on. And this is one, this actually happens to be the West Brook, where we've been working for 25 years or so, mostly with tagged fish, but now we're focusing more on estimating flow in the tributaries. And so we have a whole bunch of gauges, a whole bunch of gauged tributaries here in this very small system. And what we can see here is flow over time, runoff over time. So this is flow scaled by watershed area. So if we could use watershed area to predict flow perfectly, all the lines would be on this would all be on this black line, which is represented by this black dot. It's at the bottom of the tributary. But as you can see, there's a ton of difference across tributaries over time. And the sort of scary thing is there's a drought a couple years ago in New England, and you can see that the variability gets higher when there's more drought. So there's more risk to populations. There's more variability across populations. And one way we can think about this is we can use this reference gauge that's in the middle and look at streams below and streams above. And the ones that are below are most likely to be more vulnerable, and the streams that are above are less likely to be vulnerable. And this can be useful for combining this kind of flow information with temperature information. And that's what the state of Massachusetts has been doing recently. They were designating climate refugia based solely on temperature, but now they're combining both flow and temperature because I think as Than said, you have to be able to breathe. So you have to have water in the streams, and you have to have a decent amount of water in the streams to think about it as a potential refugia. But the idea is we could combine flow and temperature together if we can get good estimates of, or decent estimates of flow in a lot of places. And right now we don't have that. So yeah, the idea is, can we come up with models for flow and temperature together? So there's some existing models out there. We have our ecosheds, this Bayesian regional model, which is fine at a regional scale, but when we drill down to very small streams, it's not that great. Frankly, because of this heterogeneity, and also this model is not network aware. So in the future, with temperature in particular, what we'd like to be able to do is we're evaluating these kinds of models that are used in the Northwest called SSN, or spatial statistical network models. And they have a new Bayesian version, which just gives us a little bit more flexibility. So that's one thing we're evaluating. But then the other potential is a joint flow temperature model that's called a process-guided deep learning model. And this is getting worked on a lot by USGS, especially in the Delaware River. And this is an AI, artificial intelligence, machine learning kind of model. And the deep learning part means it has lots of layers that the data go through. And the process-guided part means that we don't let the AI go wherever. We constrain what it can predict and what it can understand, essentially based on physical processes. So basically physics. So we don't let it go into crazy places. And maybe we're also working with the folks at University of Pittsburgh to see if we can combine the two to get kind of the benefits of both of those. So that's a possibility in the future. For flow, we have things like stream stats as part of USGS and many other ways to estimate flow in smaller streams. But we're hoping that this joint flow temperature process guided kind of approach could work. And as I mentioned, this is being tested out in a lot of detail in the Delaware River Basin. And if you want some details, you could search for Delaware River USGS and process guided. They have a really nice webpage that describes how these models work. The trouble is they're not focused on headwaters in this big approach. So we're talking to them, I think, next week about the possibility of doing some of the things I'm going to show you in a minute in this big Delaware River project. Okay, so we have some new ideas for models, but the models are only as good as the data, of course, and so we need these big data, regional databases, and we have a temperature one, and the one I'm going to tell you about mostly is the flow one, which is kind of new and exciting. So there's the temperature database as part of our ecosheds platform, and it has over 165 million records. Many of you have contributed records, and I hope you keep contributing them because they're extremely valuable to these regional modeling efforts. For flow, we don't have a regional database. There's, of course, the USGS Gages, but as I showed in the beginning, they are not in the smaller streams so much. So what we've come up with is this idea of using images from game cameras, essentially, to estimate flow. And we have a new image database in our ecosheds environment that people can go to and upload images. And soon we'll attach models to those that let us estimate relative flow from those images. So I'm going to talk a bit about that here today. The thing is, these AI ML models are very, very data hungry. They need a lot of data. So for these flow estimates to work okay, we need at least a year of data and at least hourly. So that's a lot of images. So thinking a little bit more about estimating flow in the headwaters, this is often what we have. We have a USGS gauge downstream, but then we have all these tributaries upstream. And as I mentioned before, we could estimate easily what's happening, and this is what StreamStats does in each of these tributaries. If flow was a function of catchment area, basically we could divide the flow that's here up into all these parts based on the area that the streams are in. But as I showed you, that's not the case. So what we're imagining is we have a whole bunch of locations along here where we're able to estimate flow. So this is a bit of an exaggeration. Probably we'd never do this many, but what I'm going to show you, it would be possible to do that many if you really wanted to. And the other reason, I just popped this in here just before this talk after some of the discussion earlier about the importance of flow and growth. What this is a paper we're just about to submit where we're breaking down what contributes to growth for juveniles and for adults. Things like temperature and flow and the abundance of brook trout and other species. But the thing that really jumps out here is the importance of flow in a small stream system for growth for the adult fish. So if we want to understand growth, we really need to understand flow. So how can we get flow data where the small streams are? There's a few things we could think about, including remote sensing, which would be great. It would be easy. There's tons of it around. The trouble is we have these small streams and they're often covered, obviously, in the summer by leaves and the tree canopy. So it's just not going to work for these smaller streams. USGS gauges are great, but they're expensive and there's just so many streams. That's just never going to be practical. Models, like I've mentioned, these local characteristics can dominate, and often the flow is not a function just of area. So this led us to the idea of using these game cameras, which are relatively cheap and easy to set up and easy to run, to collect images and then see if we can estimate flow from those images. So what do we need to develop a gauge system for small streams? We need three things. One is a database, and I'll show you that quickly. Input data for the models, and this can be either we have local flow data, in which case it's, doing the imagery isn't that valuable because we have the local flow data. But most of the time we won't have local flow data. So that's what I'll focus on, is the ability to get information from these images when we don't have the local flow data. And then we need the AI ML models to actually estimate stream flow from the images. So we'll just work through these three things real quickly. This database is online. Now you can go to it, and if you have images, you can upload, or you can just explore some of the images that are out there. So it's a pretty new database. It's been out for a few months, but we already have 300,000 images in there. And when people upload them, they can be public or private. So if you don't want to share your site, you don't have to, but the images will still go into the modeling. One thing that people like to use this for is just to visualize what the stream looks like at different flow levels. So this is a site where they do have flow estimates over about a year. And in this application, you can zoom into a time period. So we've zoomed into just before December here, and we see this little tiny flood event. And you can almost see the stream kind of breathe in and breathe out. It's really fun to watch these time-lapse videos from all these different locations. The input data, as I mentioned, if we do have flow data, which sometimes there's imagery at existing gauges, or people have their own flow data, the input data into the model can be the flow estimate of itself, and the model score, what we get out of the model, will be an estimate of flow itself. So that's a good case, but again, it's not going to be very useful if we have to have flow data everywhere. So when we don't have flow data, what we've come up with is that the input data is manual image pair rankings. So what we have is the people that care about the place, who uploaded the images, will be able to go through and rank each pair, whether the image on the left has higher flow or the image on the right has higher flow, or they're about the same. And it turns out, as I'll show you in a minute, that doing just that and feeding that into the model is actually enough to train it to be able to rank all the images in the data set and get us an estimate of relative flow, which is really astounding to me that it works. But as I'll show you, we get remarkably good predictions. In this case, the model score, the thing we get out of the model, is an adjustable relative flow. So it's not absolute flow, because we don't know that. But it can be adjusted to absolute flow if we have some data on absolute flow. So we're exploring ways of adjusting. And then the third part is the AI ML models. So I won't talk about these in much detail at all, but they're these deep learning models, and we're taking these pairs of images, basically mushing them, slicing them and dicing them, turning them upside down all around, and finding parts of the images that have something to do with this pair ranking, whether one image has higher flow or not than the other. And again, once all that's together, we can get estimates of relative flow for all the images in the data set. So we think we have to do about 1,000 pairs, and that can take a few hours of someone sitting there and doing a pretty boring job of annotating these images. But here's the good news. Here's two results from two approaches. On the top, with the regression approach, when we include the flow data, and here on the bottom, when we're just including the ranking, we're ignoring the flow data that we have for this location. So on the top, the driver is known flow and the response is absolute flow. I'm just showing score here to be able to compare. And what's in this graph is the discharge is the measured flow in the black line. And then the red line is the prediction. And you can see we get really pretty good concordance between the two. The red line doesn't always capture the peak of the flood, but we definitely see a very good pattern, good relationship between observed and predicted. And the crazy thing is down here on the bottom, when the driver is image pairs and the response now will be relative flow, it looks about the same. We get very similar predictions to when we actually use the flow information. So that's really, really powerful. So we can now estimate relative flow. Again, this idea of relative flow, which is ranked from 0 to 1 or 0 to 100%. By the algorithm, and get patterns of flow over time. So relative flow could be, and we're still exploring the value of relative flow, but it's definitely useful for understanding the timing of peak flows or identifying intermittent flows, especially identifying when flows are really low for a long time, or identifying obstructed flows in more urban settings. So imagine we have an estimate of relative flow. What if we want an estimate of absolute flow? And this could be important for network models when we want to be able to route water down the network, or any case where we need actual flow. So this sort of optional step, if we have flow observations, we can actually use those flow observations to scale the relative flow that goes from 0 to 100 to whatever the absolute flow distribution is from 5 to 30. So as I mentioned, we're still exploring this, but I think that it has real potential to be able to get us absolute flow. We just don't know right now what the minimum requirements for the number of flow observations to characterize basically the distribution of flow for a site is, but that we're working on that. Okay, so when we're thinking about data and models for headwaters, clearly we need high resolution. So I encourage and would love it if everybody could get all the temperature data they have into this, into our ecosheds database, this regional database. And if you have image data, or if you think you have locations, you might want to be able to estimate relative flow or maybe even absolute flow. Please think about uploading image data to this new image database. And as I mentioned, we'll be integrating these models that we're still working on into this. So you should be able to get estimates of relative flow within 6 months or maybe a year. And there's so many of these small locations, these headwaters out there. It's a little daunting to think about, what to recommend for people to do. But I think we could think just like they're doing in the Delaware River, which is a focal watershed. We could think about smaller focal basins that people could work on. We'd love to work with you on that. So if you had a stream like Shavers or someplace you really cared about, you could think about a network of these cameras out there. And it would be best if that was upstream of an existing USGS gauge, so you have absolute flow down below. And other folks in USGS are working on networking these game cameras together. There's some that have wireless capability. So all the images could actually be uploaded to the cloud directly. And we're thinking that could be really exciting for flood prediction, where we could, in theory, have all these images being shot up to the cloud and have real-time estimates of flow. And even have it adaptable. So if we know a storm's coming, you start taking an image every minute or every half minute or something instead of every 15 minutes. That'd be a really exciting thing to think about. And the departments of transportation seem pretty interested in this. But it'd also be really useful, if you have a site you care about, a single site that's anywhere, that could also be really helpful for estimating flow. And right now, we basically need images from as many different places as we can to understand how these models work. And then, ideally, if we can estimate flow now from relative flow. So what we need to learn is how we can integrate these into these joint flow temperature process guided deep learning models for headwaters, because they're not focusing on headwaters right now. And that's our big push, is to integrate that. And then also thinking about how to integrate the image data directly into these joint flow temperature models is really exciting to think about. So that's something we're working on as well. And overall, what we're hoping that this can provide in addition to other things where whenever you need flow estimates, is improved characterization of climate refugia with the combination of temperature and flow, and really helping us understand heterogeneity in a whole bunch of places. And the folks on the West Coast have talked a lot about the value of the portfolio effect. So having multiple kinds of habitats, these are the places they want to protect. So we can think about this on very small scales when we understand the small scale variation in flow and temperature together. So that's the goal, is to be able to understand that in as many places as possible, and particularly in places that people really care about or have to make difficult decisions on. This is funded by a bunch of great groups, and we have a big proposal into the Northeast Climate Adaptation Science Center that we hope to hear about soon, that we could keep going on this work. And this is my dog Ella, and this actually started 5 years from this bridge where I was taking daily pictures with my cell phone and showed them to some people, and we started talking. Well, maybe we could estimate flow from these, and that's where it all started. So never underestimate the value of taking a walk with your dog and what it might turn into. And I will stop there.
Thanks, Ben. Time for a question or two.
Just more of a comment, Ben. Great presentation. Would you be available to chat with me offline maybe next week?
Absolutely. Yep.
Okay, I'll send you an email or something.
Okay, great.
Chat.
Hey, Ben. Chad Landris on the Mon National Forest. That was awesome information. I'm kind of thinking about it from the other side of kind of management implications. A lot of the work we do is looking at roads and trails to restore those to get surface water that used to be groundwater back into groundwater. And I'm thinking about it, this is an application that could be used using these models, inserting that kind of information into your models, and then using some camera validation to see if we're affecting flow in some of these smaller catchments.
Yeah, absolutely. And we've trained these models to estimate and understand flow, but it can be all kinds of things. It can be water, no water for ephemerality. Kind of the extreme version of flow, no flow. It could be something about all the woody structures people are putting in. When do they get blown out? You probably don't need a model to figure that out, but there's a lot of things that you could imagine you could train these models to work on, and flow's just one of them. And the part of just flow itself is one part of it. So yeah, I'm really excited to see where this goes with all the great ideas that might come out of it.
Yeah, I will put my name in the queue for next to follow up with you then.
Awesome. Yeah, that'd be great.
Sorry, Ben, we didn't mean to pack your schedule next week,
That's what it's all about.
Yeah.
Hey, Ben, Jason Coombe.
Hey, Jason.
I have a question on your training data set that you showed in that. What was the duration and frequency of those photos taken for that?
Every 15 minutes for a year.
Thank you very much, Ben. We're going to move on to Jake Lemon, the next presenter.